A quantum computer is not just one strange chip in a cold metal box. It is a whole machine built around keeping fragile quantum states alive. At the center is the quantum processor, or QPU. This is where the qubits live. In some machines, the qubits are tiny superconducting circuits. In others, they are trapped ions, neutral atoms, photons, or silicon-based spin systems. Different companies are betting on different designs because nobody knows for sure which one will scale best. Around the processor is the control system. A normal computer sends electrical signals through circuits. A quantum computer has to send extremely precise pulses, sometimes microwaves, sometimes lasers, to push qubits into the right state without destroying the calculation. Then there is the cooling system. Many quantum computers, especially superconducting ones, need dilution refrigerators that cool the processor to temperatures close to absolute zero. That is colder than deep space. The reason is simple. Heat creates noise, and noise ruins quantum information. IBM describes its modern systems as combining cryogenic infrastructure, qubit control electronics, and classical runtime servers into one hybrid machine. There is also the readout system. At the end of the calculation, the machine has to measure the qubits and turn the result back into ordinary data. This is harder than it sounds because measuring a qubit destroys its quantum state, so the timing has to be exact. Finally, there is the classical computer sitting beside it. Quantum computers do not work alone. A normal computer still prepares the job, controls the hardware, checks the errors, and interprets the results. The future is likely to be hybrid, quantum processors working beside supercomputers, not replacing them. That is why IBM talks about quantum-centric supercomputing. Its roadmap focuses on linking quantum computers with high-performance classical computers, and IBM says its 2026 goal is to demonstrate early examples of quantum advantage using quantum hardware and HPC together. Google is chasing the same mountain from another side. Its Willow chip is a 105-qubit superconducting processor that showed a major error correction result. As the error-corrected qubit got bigger, it became more reliable instead of worse. Google calls this a key step toward a useful, large-scale quantum computer. Microsoft is taking a riskier path. It is working on topological qubits, which are designed to be more naturally protected from noise. Microsoft announced its Majorana 1 processor in 2025 and says it is working toward a fault-tolerant prototype through DARPA's utility-scale quantum program. But this approach is controversial. Some researchers remain cautious about whether Microsoft has fully proven the physics behind the claim, so it is one of the boldest bets in the field rather than a settled victory. Amazon is also in the race. AWS announced a prototype chip called Ostalot, based on cat qubits. The goal is to reduce the burden of quantum error correction, with Amazon saying the design could reduce error correction resources by up to 90%. And it is not just tech companies experimenting with quantum. JP Morgan Chase has one of the most serious finance teams in the field. It says it has built an internal quantum research team working on algorithms for finance, AI, optimization, and cryptography. In 2025, JP Morgan Chase, Quantinuum, Argonne, Oak Ridge, and the University of Texas announced a certified quantum randomness result, which matters because strong randomness is important for cryptography. Cleveland Clinic is using quantum with IBM for healthcare and life science research. IBM says the Q4 Bio Challenge is aimed at developing quantum algorithms for healthcare that could run on quantum computers expected in the next 3 to 5 years. BMW has been researching quantum computing since 2017. Its focus includes industrial problems like manufacturing, materials, and optimization. Logistics companies are watching closely too. DHL has explored how quantum computing could affect routing, supply chains, and optimization, although the company also notes that practical use is still years away. That is the important point. Quantum computing is not science fiction anymore, but it is also not fully useful yet. Most real-world work today is research, pilots, benchmarks, and early access programs. The machines are still noisy. They still make too many errors. They are still expensive and difficult to operate. But the direction is clear. IBM is trying to connect quantum computers with supercomputers. Google is trying to prove large-scale error correction. Microsoft is betting on topological qubits. Amazon is trying to reduce the cost of error correction. JP Morgan is preparing for finance and cryptography. Cleveland Clinic is exploring medicine. BMW is testing industrial use cases. DHL is watching logistics. So quantum computing matters because the world's most powerful companies are not treating it like a toy. They are treating it like the next specialist engine for problems too complex for normal computers. Not every company will win. Some hardware designs may fail. Some promises may take decades longer than expected. But if one group builds a reliable, fault-tolerant quantum computer, the impact could be huge. It could change how we design drugs. It could change how we build batteries. It could change how we protect data. It could change how we model the tiny world that normal computers struggle to copy. Your phone will not become a quantum computer. Your laptop will not be replaced by a fridge full of atoms. But the systems behind medicine, security, finance, logistics, and advanced materials may one day depend on machines like this. That is why the race matters.